In this video, I introduce asynchronous advantage actor-critic model. Asynchronous advantage actor-critic model trains a single model using multi-threads on a single CPU. So use the A3C model, we get two major benefits. First one, because we use multi-thread, each thread holds the complete model parameters and can visit the complete training data set. So when each thread picks the sample from the data set, and then it will break the relationship between the samples in a sequential sampling. So we don't need, use the experience replay to break the relation between the samples in the sequential sampling. That's the first benefit, because we don't need the experience. We don't need the experience replay. So if we use the experience replay buffer, we have to, use the offline. Here, just use the online. That's fine. Second, in the distributed reinforcement learning training, we need set up one server as the parameter server, rest of them are model server. So we need to fetch the information between the parameter server and the model server. This is model parameters from a parameter server to the model servers, and we need to send this gradient from this model server to the parameter server. But here, because all the threads they share use the shared memory, that means they visit the same memory, and we can use the global variables. That means we don't need to exchange, no combination cost. That means we don't need to send any information from one thread to another, because they can visit all the global parameters. That's two major benefit from the asynchronous technique. First, let's see asynchronous one-step Q-learning. That means we use Q-learning to train a reinforcement model to find the optimal policy. So in Q-learning, we use two networks. One is a Q network, another is a target network. So yes, that means in A3C, we need to run two networks on each thread. And this we need only, but we only need to train the Q network. And the parameter for this target network is model parameters copied from this Q network, but not every step. We need that's what we call slowly change. That means, for example, every 1,000 steps, we copy one, copy the theta to the theta minus to this target network. And then we train this Q network and use this target in a supervised manner, and we generate the A. Then we send the A to the environment and get this reward, and then we use this next state as an input to the target network. We generate this target used in the Q network training. Here we just we need to wait until we receive all the gradient from each thread, and then we update the model parameters. So that's the idea when we use asynchronous method in the one-step Q-learning method. Then next, let's see the asynchronous advantage actor-critic model. First, in the A3C model, you still use the double deep queue network. That means we still need to use the two networks. But right now we first we in the queue network we have two output models. One is to output the policy, another one to output the value function v. So in each time step we need update the model parameters by using this gradient. So-called the policy gradient. That means we use this policy gradient to represent the gradient of the objective function. Here, this is the advantage function. This advantage function is calculated from the temporal difference. This is the target, and this from 0 to keep -1. Here, this is the terminal state. And this is the current, this is the state value function at the current state. So we use one network because we this policy network and the value function network V, they share the same input, and they share the same convolutional network, but they have their own output module. Here it shows the basic architecture of the A3C model. Here is each thread we run a complete model. Includes one queue network, one target network. They can access the entire training data set. And that's why we don't need the experience replay method here. And here we have this input same for all the threads, and they each thread they run a model and get this. For example, this is the policy output module. This is the state value function v value. I just run just this like an Actor-Critic. This policy module uses as an actor, and this value state value module uses as a critic to evaluate the policy generated by this actor. Actually, they work each other because we will train them the model, and at the same time we generate the convergence, the policy pi and the state value function. If one of them is not okay, then both of them, we have to train both of them, make sure all of them reach to the convergence. Once they reach the convergence, we can, we have this model, then for input, we will get the optimal policy and the optimal state value function. Right now, each thread just run part of the samples. So we use one to collect all the gradient, and we put them together, generate the final pi and the policy and the state value function. Here also mentioned they use the forward view. Forward view is here. It's not the eligibility tracing method. Right now, forward just from a current state, we go to the future and use this update. For more details, please check with this reference. Thank you. Bye.